So can everybody see the slides?
I can.
And how about the transition?
Looking good.
Okay, great. Okay. So I think we should start. And first of all, thanks for your efforts to finish the homework one. Those are all about decision trees that might take you quite amount of time, and because they are very important. Your implementation of decision trees will also be used to implement your boosting and bagging in homework 2. You might have noticed we have released homework 2. So as long as you have you're satisfied with your decision tree implementation, then it was pretty uh, straightforward to extend it to implement your either boosting and baggings. And then I believe the workload for homework 2 will be uh, much smaller. All you need to do is that you implement the framework and conduct a variety of tests to, confirm the things we have discussed, like how we combine the weak classifiers together. We end up with a very strong classifier, and how either boost is immune to overfitting, right? These are something we want you to really experience it by applying your own implementation in real data sets. So again, please start doing homework 2 as early as possible. We have 2 weeks. That should be more than sufficient. But if you try to do it like 1 day before or 3 hours before, uh, you might feel like the time is really short because you have to do, even the implementation is relatively straightforward. You still need uh, uh, quite amount of time in testing all the cases and report the results. Okay. And again, please feel free to ask questions and take advantage of the Piazza forums and our TM's office hours. We're more than happy to help with you. Oh, by the way, everybody should decide which kind of projects you want to do as soon as possible. I believe the deadline to submit your project plan is approaching, right? And if you have decided the to do the competitive project, that is Kaggle competition, please try to submit some like dummy submission. Someone asked me what is dummy submission. It's basically you just randomly create a submission file where each line corresponds to test the case ID and the prediction score. That's it. And then you just look at how many test examples you have, which can be downloaded from the competition website, and then you just run the generate number, and then we'll upload it. The system will give you a number, which is the area on the curve. You'll see value. Okay. So if there is no further question regarding homework, new homework, and also the project planning, we're gonna continue with ensemble learning. We'll quickly wrap up our ensemble learning, tagging and random first, and then we'll proceed to a new topic called linear models. Okay.
I have a question about the project proposal real quick.
Yeah.
So if we have a partner on Canvas, do we both submit the same proposal, or does just one person?
Just
have
one
to
person will be fine, but you need to notify our TMs.
Okay.
Yeah.
All right, thanks.
No problem. Any other question?
Yeah, one other question. If we're doing the Kaggle competition, there's no file we need to submit on Canvas, correct?
No. You need to, but I believe you need to fill out a Google spreadsheet, right?
Yes.
And to let TMs know who you are and what are your accounts.
Perfect. Okay, thank you.
Problem.
If you are a team, do you need to fill out the spreadsheet or no?
If you what?
If you are a team for the exploratory project, do you need to fill out the spreadsheet?
No. That's mainly for the Kaggle competition.
Gotcha.
If
Okay.
if you decide to do the exploratory project, you don't need to fill that form.
I already have made an entry on the spreadsheet. Should I remove it?
If you specify that you're doing, the exploratory project rather than Kaggle competition, I think you can leave it.
Gotcha. And how best should we notify the TMs that we're doing a exploratory project?
You just upload your one-page project description in Canvas.
Okay, so just uploading it is enough. Like me and my partner, one of us uploads it and it says both of our names or something.
Yeah. It's better for you to send them an email. But if it's not, our TMs will try their best to record everything. But in case that they kind of like miss writing down your name on that, you can send them an email. Any other question? Okay, great. So on last Thursday we mainly introduced the bagging, which is another dominant strategy for ensemble learning, right? So bagging is actually even simpler than ADA boost or boosting type methods, right? So suppose this is a general framework of bagging. Suppose we have a set of M training examples, and again we can perform like big T iterations. However, all those iterations can be done in parallel, where in each specific iteration, we draw a new set of training examples from the original training set. How can we draw a new set of training examples? We draw like M prime samples uniformly with replacement. So basically, we just used our original training set as kind of like a data source, right? And then we just randomly sample the examples from the data source M primes times. In this way, we create a new set of training examples, and based upon this new set of training example, we train a classifier with any classifier. We train a classifier with any model, right? And finally, we can collect big T classifiers, and then we either take their votes in prediction or average their prediction or outcomes as our regression result. And we have emphasized what does it mean by uniformly sampling with replacement, right? So if we set M primes equal to M, such array sample training set is called Bootstrap sample. I remember because it is uniform sampling with replacement, there can be some duplicate examples. That doesn't matter. And this sampling procedure is justified in statistics. It is called Bootstrap sample. And we have illustrated why doing this works, right? So, oh, by the way, the most commonly used classifier, base classifier in bagging is decision trees. So basically, inside each iteration, right, when we collect a bootstrap sample from our original training data, right, we can learn a decision tree. And here's a very different point from boosting and ADA boost. we're gonna learn this tree without any restriction. We just expand the tree as large as possible, as wide as possible, and until you meet the stopping cases in the original ID3 algorithm. You do not need to control the depth and width. You do not need to prune the tree branches. And finally, you just take an average of all the tree predictions to get a final prediction. Of course, if you're doing classification, you just do the final vote, right? And then we explain why this works, right? This seems like really straightforward, right? You just in each iteration, you just uniformly randomly sample a set of new training examples. Based upon that, you just grow arbitrary large tree, right? And then you just take the average of all the tree's predictions, why it works, right? So we justify the rationality of this by using this bias plus variance decomposition, right? Specifically, we look at the expected square error, right? So for any particular test example X star, right? And I want to say what's the square error of using our learn tree to predict or learn any classifier, right? To predict X star, comparing with the ground truth label, right? And we take expectation with respect to the data distribution, meaning that, okay, suppose we just run our training, our model on the collected training set many times. Each time we just use data distribution to generate the same size of trained data and train it. We get a learned classifier, make prediction and see what is the square error, and then we'll take the average, right? That reflects how good your classifier works in learning this hypothesis and in prediction, right? So by using some kind of like standard tricks in statistics, we show that the expected square error can be decomposed by a summation of two terms. One is called bias term. The other is called variance term, right? So the bias term is a square difference between the ground truth prediction and the expected prediction of the learned hypothesis. So what is expected prediction? Meaning that, okay, if I train my classifier on one particular data set, I got one hypothesis, right? Then I can make one prediction, right? So suppose I do this numerous times, right? Each time I use the original data distribution to sample another training set, then I learn a hypothesis and make a prediction. Then I average all possible predictions under this training data distribution and say how the difference between my average prediction or expected prediction and the ground truth prediction. I take square. This is called bias. Right? And the other term is a variance, meaning that, okay, because whenever I change the trained data set, my learned hypothesis will change as well, right? Then accordingly, the prediction might change as well. I will look at how these predictions can vary along with data distribution. This is called variance. So it's interesting to see that this variance term has nothing to do with the ground truth label. Right? It actually reflects some internal or intrinsic property of the learned classifiers. Right? So from this bias plus variance decomposition, what we can say is that the more complex or more expressive your learning model, the smaller the bias you have. Why? Because you can imagine that you have a highly complicated machine learning model. So every time we will feed this model a particular training set, it will try its best to perfectly fit the training set, right? So every time it tries to fit all the training examples in the training set. So on average, it will give a much closer prediction toward the ground truth prediction because the training examples, the labels of training examples are calculated from the ground truth function, right? But in the meantime, such strong classifiers or such expressive classifiers will be very sensitive to the change of training examples because no matter in what kind of cases, they always try to perfect fit to the training set, right? So imagine that we will switch to another training set where only a few training examples are changed, right? And to perfect fit the change of these examples while maintain the perfect fitting of the remaining examples, you can imagine the structure of model or the parameters of model can be changed dramatically, right? The consequence will be, okay, complex model usually have large variances. So you can see that there's no free lunch. If you choose a complex model, choose an expressive learning model, well, you can get smaller biases because your perfect capability to fit the training data. But at the same time, because you're so sensitive to the change of training data, you got a large variance. On the other side, if you choose much simpler model, right, like the linear models, which we're going to discuss later today, right? So it doesn't fit the training data very well. It always has some kind of a gap between the ground truth prediction and your prediction, your own prediction on the training set. Means that your bias is relatively large. At the same time, it implies that when you change the training examples a bit, it might not affect the learning result at all. Why? Because it's not sensitive to the change of the training data, because its aim is not to perfectly fit or perfect predict all the training examples. So you can see, okay, although the simple classifiers, the simple machine learning models have large bias, but its variance is reduced, right? So you can see this is a kind of trade-off, right? So we're not, in practice, we're not arriving any of these extremes, right? We're not trying to find extremely powerful and expressive models which have very small biases, but pretty large variances, or in other extreme, like you have two simple classifiers where your bias is too large, although your variance is approaching zero, right? Both the extremes are not ideal. Instead, we're always trying to find a good trade-off, the best trade-off, which you give a smaller summation of the bias and variance. Okay, so by understanding this structure, right, of this expected square error, we can take a look at our bagged decision trees, right? So first, decision trees itself are complex classifiers, right? Meaning, imagine that if we do not control the growth of the tree, decision tree will always tend to overfit, right? The ID3 algorithm only stops when all the examples in the current node are labeled as the same, or you don't have enough attributes to split the data set, right? So decision trees always tend to overfit, meaning that, okay, it has smaller bias. And also, you can imagine that by slightly changing a few training examples, the structure of decision trees will change dramatically, right, to overfit the whole new data set. Right? So the decision tree has large variances. And how can we improve the expected or the generalization error of decision trees? Right? Consider the bagging strategy. Suppose I have a bag of like 100 trees, right? Each of those trees are growing wildly, right? Very large, very deep, and so on, right? So we can imagine that each of those trees, when they make predictions, they have a small bias but large variance. But if we do this average, right? Because we have the bagged trees, right? When we do the prediction, we do their average. An average of this 100 trees, their bias will still keep in the same skew, right? Because each of those trees have a small bias. If you take the average, their bias is small as well, right? But what about the variance? The variance will be significantly reduced, right? Why? Could anyone?
So if we consider it as random variables, average of random variables, the variance reduces by the number of independent variables added.
Yes, exactly, right? So this is just like if you take analogies, it's like analysis of random variables, right? So in our statistics, we all learned that if you're given like n IID random variables, identically distributed independent random variables, right? If you take the average, their expectation does not change at all, right? It's the same as any single expectation of any single random variable. But if you take the variance of their average, the variance will be largely reduced, right? For n IID random variables, the variance of their average can reduce the variance of single variable by a factor of 1 over n, right? So this is like a basic knowledge from the statistics, right? So similar kind of arguments apply to baggage decision trees. Although, of course, we cannot say all those trees are IID because their training data can kind of have some overlapping training set, right? So they do not achieve the ideal case where all the trees are IID, right? But as long as they're not that correlated, the average of their prediction will have much smaller variance as compared with each single tree's prediction, right? So now we can see when we do the average of baggage trees, we maintain the same level of bias. Meanwhile, we significantly reduce the variance. Then overall, we significantly reduce the expected square error, which indicates the generalization error. That's why bagging works. Okay, so this is a very important insight. Although for convenience, we only conduct such analysis in the continuous case, meaning in a regression case. But for other types of error, like 0-1, which is used for analyzed classification error, we can find similar bias plus variance decomposition as well. And also, all those arguments and logics apply as well.
I have a question kind of related to this, and going back a little bit. So a few slides back, if you don't mind going back to like the overview slide of the algorithm.
Mm-hmm.
Right. One more. One more.
This one?
Sorry, I can't quite remember where it was. Keep going back. This one. So you say, ultimately under the second bullet, you say we want to draw M prime samples from the training set, and that can be less than or equal to M, which is the total number of samples. I'm just curious, how do you select M prime, and is that going to influence the results of what we've just been talking about in terms of like variance reduction?
M primes is chosen by the user.
Is it irrelevant?
Is it relevant to what?
So I guess because I would, okay, how do I put this? So ultimately the goal of this whole bagging method is to create a bunch of different decision trees using some combination of the training data and averaging the results to get, to reduce the variance in the resulting tree. I'm just curious, how does M prime, the selection of M prime, influence that? Because would you always want to pick it to equal M, or would you want it to be really small?
No, I don't want it to be really small. So a common choice of M prime is just M.
But I guess then why not always pick it to be M?
It gives you some flexibility.
Okay.
Like, suppose you have a very large number of training examples. Say you have 1 billion training examples, right? You don't need always to run a bootstrap sample which contains the same 1 billion training examples to train a tree.
I see.
In practice, it's actually not necessary. You find that most cases, maybe a few thousands are more than sufficient. Even you add more training example, it won't improve the performance dramatically.
Okay.
So the choice of M prime just give you such kind of flexibility.
I see. Okay. Thank you.
Yeah, but usually, I mean, a most convenient choice of M prime is just simply M.
Right.
But it really, I mean, it's really, there's no rules telling you that which particular M prime is the best.
Sure. Okay.
It actually depends on your application, depends your requirement of accuracy, and depends on your, the capacity of computing power, whatever.
Okay.
But if we choose N prime to be M, wouldn't that give us the same tree over and over? Like even if, let's say, we are not sampling the whole data set, we will still be sampling because it's random sampling. We'll still be sampling like 75% or 85% of the data set that is there, right? So wouldn't that give us the same tree, like almost the same tree always?
That's a very good question. That's some problem I want to discuss later. But the issue that the problem you mentioned here is that if I set M prime exactly the same as M, and each time when you draw such M examples uniformly with replacement, it does not imply that all the new training sets are the same. There are kind of have some like I forgot, but there's some kind of like 60, I guess 60, 67.5% of chance to have overlapping. But arbitrary two training sets are exactly the same. That this chance is very, very small.
Okay. And what like depending upon how many samples we have, what is an ideal T, like total number of trees that we should have? Like is there a constant thing, or do we experiment with it, like, and
you need to experiment with big T.
Okay.
There's no rule telling which which choice of big T is optimal. It also varies along with applications.
Okay.
So I mean, this is kind of like common patterns in machine learning algorithm. There are always some kind of hyperparameters which you need to tune according to the detailed problems, specific problems. No one can guarantee a specific setting which, I mean, can give you a specific setting which guarantees you to have a best performance all the time.
Okay.
Okay, and the question regarding the general framework bagging. Great. So let us continue. Oh, sorry. Yeah. So, but as Tushar just mentioned, right? He actually expressed a kind of concern, which can be severe in practice. So, although I mean, in two different iterations, the chance that you collect exactly the same set of training data by bootstrapping is very, very small, but you still have a chance to create a highly structurally similar trees. Why? So consider in your feature set, right? There are a small set of features which are strongly discriminative and indicative, meaning that during the tree construction, they will be consistently selected by most of the trees. And for example, in the first split, they will always select feature 5, and in the second round, in the second split, they always select the feature 1 and then feature 2. So then you can see that after you collect like 10 Bootstrap training data sets, you're gonna generate 10 trees whose structures are very similar. This is possible, right? As long as you have some dominant, highly discriminative and indicative features. And the consequence is that those bagged trees will be strongly correlated because their structure correlations, right? I mean, meaning that their predictions will be strongly correlated. And remember, in our justification, right, in our proof, when the bagging strategy works well, right, when we maintain the same kind of bias, right, and we significantly reduce the variance, right? But now if the predictions from different trees are highly correlated, your variance won't be able to reduce much. Consider an extreme case, right? Consider all your baggage trees are the same. They're exactly the same. Then what is the variance? Your variance will be the same as one single tree, right? I heard someone want to say something, right? Right. So if you consider one extreme case, right? So suppose you collect the 10 trees and all the trees have exactly the same structure, then you take the average of the prediction, their variance, the variance of this average is the same as the variance of one single tree, meaning that your bagging strategy won't work at all. Right. So how can we address this problem? What we can do is to try our best to decorrelate the trees, right? To make the trees, their predictions to be as less correlated as possible. Does it make sense? And any question regarding this motivation? Because this is really important. Okay. So now how do we decorrelate or reduce the correlations between different trees in our bag, right? This comes this random forest, right? This is how the random forests were invented. We can view it as a plus version of baggage trees, right? So similarly, we assume we still run like a big T iterations where each iteration we can sample Bootstrap data set from our original training data, right? But then during the construction of each particular tree, at each split, we're not gonna always use the available and valid attributes to select the best features or attribute. Instead, each time we first randomly draw a subset of available attributes. And then we'll only calculate the information gain on this random subset and pick up the best one to perform split. And do it recursively until we finish the tree construction. In this way, you can imagine like when you construct tree 1 and construct tree 2, right? At every node split, right? You have a very large chance to select features from very different subsets, right? In this way, you're trying to make your trees to be less similar as possible. So this is a key idea. And then after we collect the T-trees, as usual, we average the predictions to make a prediction, right? To make the final prediction result or do the voting for the classification task. So here is the pseudocode from which you're gonna follow which you're gonna implement your own random forest. So let us look at the pseudocode, right? So again, suppose we're given a training set with m examples. Our feature set is denoted by this big F, right? And again, we run big T iterations, where in each iteration, we draw m examples uniformly with replacement from the training set, right? So here we assume we're using a Bootstrap sample, but as we discussed 2 minutes ago, right? So you can flexibly choose m. If you feel you don't have enough computational power, you can choose m prime samples, which is less than m, right? But as a standard approach, you can just sample the same number of training examples, right? And then we call this tree construction procedure called random tree learn to learn decision CT. And from the Bootstrap sample dataset XT and YT. And after this big T iterations, we have collected big T for trees, and we call forests. And then we vote the predictions of these T trees for classification or average the predictions for regression, respectively. Right? So this framework is the same as the baggage trees, baggage decision trees. The only thing The only difference lies in this random tree learn procedure, right? So now let us look at this procedure. So this procedure is 99% the same as ID3, except that during the recursion, right, at each node, before we calculate information gain and go over all the available training set, available feature or attribute, right, we first randomly sample a very small subset of A. So A denotes the current available attributes. Meaning that we first sample a small range from A. We denote this by G. And then we only calculate and rank attributes inside G. We find the best feature in G, and then we perform the split. And then, we grow the branches and we split data sets, and then we recursively call this random tree learn again, right? So remember, in our recursion, we need to exclude the selected feature from A. That's it.
And this subset, right? When we do the subset of A, so like G is the name of the subset, right?
Yes.
So we remove the selected feature from A. We don't remove it from G and then pass G down, right? Because we still want to be able to split on everything in the future.
Yes.
Yes. Is there a base case here where, if you have only one feature, say, coming in, like there's no choice, right? Like I guess that's fine. Because you don't want to take a subset and get 0 things, right?
No, I mean, if your A is you only have one attribute available, you have no choice, right?
Yeah.
You have the only
Is the second question is how small should this subset be? Is it a proportion? Is that what do you call it? A hyper variable? Something like we can determine when implementing the code?
Yeah, this is a hyperparameter. Again,
hyperparameter, that's the word.
Yeah. Yeah, you need to choose by yourself.
Okay.
Like it depends on your application. Like if I'm like 1 million features, right? You can set G to be relatively large, like 100, or even 1,000 might be good, right? But you only have a few hundreds features, right? Like 100 features, you might be set G to be the size of G to be only 5 or 10.
Right. And you always want it to be proportional to A, right? Like you don't want to have a constant value for how much of a subset you're going to have, right?
It still depends on your choice.
Really? Okay.
Yeah. It really depends. I mean, if you want to develop a general, let me. I think explain your fearing of the proportion of A as a way to setting the size of G might be more more favorable from software engineering view. Like you want to develop a general implementation of the random forest. Well, no matter how large your training your attribute set is, right? You can say, okay, you can choose 10% or 1% or 5%. Yeah, that is more more convenient, I think. But in theory, if you implement your own random forest, you are flexible. You can choose to set an absolute number.
It doesn't actually affect the theory behind it, right? Like that's not important to the algorithm. It will change how it works, obviously, right, and how well it does, maybe for certain data sets, but it doesn't break anything to do it with a constant value.
Yes, exactly. Any other question you understanding this? So you see, the only difference is here. Every time before you split your data set, creating new nodes in ID3 algorithm, you're going to first randomly sample a small subset of current available training features and only rank and pick up the best feature from this small subset. That's only one step. Perhaps take your extra line of code, 1 line of code or 2 lines of code to implement to plug them into your ID3 implementation. And the motivation for this is to avoid every tree to use the same a few highly indicative or dominant features to split the training set. In this way, we're trying to maximize the the dissimilarity between different trees in order to reduce their variances, right? In order to reduce their correlations, so that in our bias and variance decomposition, you have a significantly reduced variances. Okay. Any other question regarding this whole pseudocode?
What does this strategy imply about like if we're artificially restricting the number of options that our trees have, are we also sacrificing say performance or accuracy of the tree?
That's a good question. Yeah, you're right. Like if we, so in this way, you're actually trying to restrict the selection range of the attributes at each node split, right? So we're doing this is trying to decorrelate different decision trees. And when you have enough number of attributes, right, that won't change too much, because no matter how you restrict the range, right, as long as you keep splitting the data sets, growing the tree, finally you're going to overfit the training set, then your bias term doesn't change, because each tree is still trying to fit the training set well. You're going to have a good variance, a bias, right? But by using our random selected subset to split the data set and grow the trees, we can significantly reduce the correlations between different trees, right? Meaning that we can significantly reduce the variance of the average of the prediction. And overall, we can reduce the expected square error.
Yeah, I definitely see that, how the bias won't change because you're growing the tree until it's finished, right? Until it's completely overfit, right?
Yes.
So I guess the only cost of this is if we're choosing, we're limiting our heuristic, and so we're going to have probably bigger trees, right?
Yes. Yeah, that's something I just want to explain to you.
Mm.
Yeah, of course. You might, if you restrict the range of nodes to select to split, right? You might have to grow more grow more branches and grow more splits. Any other question?
Sorry, just one other kind of just like conceptual idea with this. So basically what we're doing is we're forcing, because we're going to sample from G, we're basically forcing it so that every tree has to be different, because essentially it's only every time it's going to be randomly picking from some different set of options. And so this is going to basically force us to create a wider variety of trees.
Yes.
Okay.
Yes. Exactly. And we're trying to force the generation of various trees is to, again, reduce the variance. Otherwise,
Right.
if all your trees have the same structure, the variance doesn't change at all.
Right. Because yeah, we want to consider as many options as possible to help us.
We want the diversity of our trees.
A diversity, yeah, exactly. Cool, thank you.
Okay, any other question? Because this is really important. You're gonna require to implement this random forest. Okay. So now I have finished the ensemble learning topic, right? What I'm saying, we have saying two widely used and very popular dominant techniques in ensemble learning. One is boosting, one is bagging, right? Boosting is kind of sequentially learn a set of weak learners, right? Where how do we learn different weak learners? We're trying to readjust the sample weights, right? And bagging use a more straightforward way, right? We resampling the training set by using uniform sampling with replacement. And bagging can be justified in another way. Okay, so that's all about the ensemble learning. So now we're gonna start with another topic. So can everyone see the new slides? linear models?
Yep.
And how about the transition of the slides?
It looks like it's still working.
Okay, great. So today we're going to talk about linear models. Linear models will take a pretty much portion of our whole semester because it serves as like fundamental role in machine learning. So although it looks like pretty straightforward, it's linear models, right? But actually there are many different learning algorithms of linear models, and based upon linear models, we can extend them to be much more complex nonlinear models. And you all will also see how the computational learning theory motivates the development of more powerful linear models like max margin linear classifiers. So before we proceed, we're gonna look at the bigger picture again, right? This is a checkpoint. Just review what we have discussed so far, right? So right now we're still under the umbrella of supervised learning, right? So in our training set, our training set are a collection of labeled inputs and outputs. Then we feed the training set to our learning algorithm, and this training set will guide a search procedure of our learning algorithm, and our learning algorithm will return some hypothesis, right? This is our learning classifier. Given a new example, we use our learning classifier to give the prediction, right? So underlying this, under this framework, we have viewed several specific learners, right? Decision trees, boost, baggage trees, and the random forest. I will say quite a few later, right? Throughout this whole semester. And also we have learned several general concepts in machine learning, right? What is overfitting? What is pack learnability, right? So far, any question regarding, what have we discussed so far? Okay, great. So whenever we look at a new topic, we always try to go through this checkpoint and to ensure that everything we have willed and we learn is kind of organized, organized way. It's not messy, right? So what will we talk about linear models? Right? We'll first give the definition of linear classifiers, and we'll talk about expressiveness of linear classifiers. Namely, what kind of functions do linear classifiers express? And then we'll proceed to the learning algorithms. Right? So we'll first address how do we use linear models to predict continuous values, namely regression. So we'll introduce the widely used least square method. And then we'll proceed with a variety of different linear classifier learning algorithms like perceptron and support vector machines. Okay, so first we'll introduce the definition of linear classifiers, and then we'll talk about the geometry of linear classifiers, and then we'll give some like simplified notation of linear classifiers which are used everywhere. So to introduce linear classifiers, let us look at this set of training examples. Right? Suppose we have blue circles and red triangles distributed in this plane, right? And they represent positive and negative examples. And we want to learn a classifier which can separate the blue circles from the red triangles. Intuitively, we can draw a vivid curve, we denoted by A, right? Which can perfectly separate every blue circle from the red triangles. Right? This is one way of doing so, right? But a more rough way or coarse way of doing this is to draw a line. Denoted by B, right? Line B can also separate the two types of examples. Right? So now here comes the question, right? Which one do you prefer? Or which one do you like more?
The curve looks like it's overfitted, so I'd be worried about future examples getting messed up with that.
Yes. Right. Yeah, you hit the point, right? Any other supplement?
Yeah, I'd also say the line seems a lot easier to solve for and represent mathematically, and that's just and it's still very accurate.
Yes, exactly right. So compare with compare A and B, right? Obviously, if you use A to fit the training data, your training accuracy will be 100%, right? B is not as accurate as A, but B takes much less risk of overfitting. Right? So remember the overfitting we discussed before, right? If some examples are actually corrupted by the random noises, then curve A will be bothered a lot more, right? In predicting future examples. We can take a look at these two examples, right? Suppose the blue circle here is actually not blue circle, right? They are corrupted by, it is corrupted by some random noises. It was supposed to be some red triangle, right? And because of some random noises, its label is flipped, right? And now, if we have happen to see a new example, which is the red triangle again, right? Then curve A will make wrong prediction. Oh, sorry, we can take a look at here, right? And here, make wrong prediction. But for line B, there isn't any such a problem. It is because it's much more robust to the noises. That's why we not in all the cases would prefer the more vivid, seemingly more accurate classifiers. Instead, we often choose a simpler but more robust classifiers like linear classifiers. Similar argument can be applied for regression case. Suppose these are our trained data, right? So x-axis represents the input and the y-axis represents the outputs, right? So obviously, I mean, if we want to fit the trained data, we can find a curve which can exactly go through every training data point where your training error is simply 0. Right? But obviously, it also runs some kind of overfitting, risk of overfitting, right? We can choose another much simpler regressor, which is simple line, which pass through this training set. Right? Obviously, the training error of line B won't be 0. But consider a case that where this outlier, right? This outlier is actually corrupted by some noises, right? So if we remove noises, the actual output should be around here. Then if we have a test example surrounding here, right? Then when you use curve A to make prediction, you can imagine the error is very large. But if you use line B, although the training error is not 0, right? But you can reduce a lot of the training error, test error. Why? Because it is much less sensitive to the noises in the data. Okay. So this is just a simple illustration of why, although those kind of linear models seem straightforward, it is often a choice in practice, because in real world, noises, mislabeled examples, corrupted examples are ubiquitous. We need some more robust classifiers or regressors. So now we're gonna give a formal definition of linear classifiers. Suppose our input is an n-dimensional vector x, and output is a label, which is either -1 or 1. And we call a classifier a linear classifier or a linear threshold unit if we classify an arbitrary example x using a width vector w and bias parameter b using the following classification rule. So the output is the sign of a classification function, where this classification function is the inner product between the width vector w and input vector x plus the bias B. Okay. So basically, it implies that if your classification function is no less than 0, your prediction will be 1. Why? Because the sign is positive, right? Otherwise, if your classification function is negative, your sign is -1, then your prediction is negative. So any question regarding the definition of linear classifiers? So everyone feels comfortable? Okay, great. So linear classifiers have a very elegant geometry view, right? We're gonna use this geometry to illustrate many properties of linear classifiers and also illustrate the main idea of several elegant learning algorithms, right? So suppose this is our positive examples and negative examples, right? And our classification rule actually determines a boundary. This boundary actually separates all the positive examples and negative examples. So how do we define this boundary? So this is an equality. Namely, the classification function is 0. So remember, the classification function is a linear function, right? So this equation actually defines a line in a plane, right? From what we have learned at our high school, right? It's high school geometry. And the line which is perpendicular to this classification boundary is actually the weak vector. Why? Why? Let us just try to recall what we have learned before, right? In our high school or in our, I believe it is in high school, right? Why? This weak vector, W1, W2 is perpendicular to our classification boundary.
So the dot product between vectors and the axis, like x1, x2, is equal to 0. Like that's how line and planes are represented. They are represented by normals.
Yes, exactly, right? So let me briefly explain why it is correct. Sorry. So if we, to show this, right? So you just need to check a little bit, right? So if we draw arbitrary 2 points, right? Pick up arbitrary 2 points, say Z1 and Z2 in this classification boundary, right? So how do we represent the vector which connects Z1 and Z2? We just subtract Z2 by Z1, right?
Yeah, Z2 minus Z1.
Yeah. So actually, any line which is in parallel to this classification boundary can be represented in this way, right? You just pick up arbitrary 2 points, non-overlapping points on this boundary and subtracting them, right? You get a line which is in parallel to this classification boundary, right? What you need to do is just to show that, okay, this line, this vector, is inner product with the weak vector is 0, right? This is the definition, right? If this line, this vector is perpendicular to this vector, you just need to show their inner product is 0, right? And how to show that is straightforward by using this equality, right? Because Z1 stays on this classification boundary, so it satisfies this equality, right? Z2 satisfies this equality. You just subtract the two equalities on the left-hand side, right? Then you immediately obtain this one, right? On the right-hand side, 2 zeros, their difference is 0 as well, right? Then you show this. Okay, so just leaving you as exercise to review the geometry, right? So we can see that, okay, by using this classification boundary, we can say where the positive examples locate, where the negative examples locate. So basically, all the examples locate here, meaning that they're, the vector representations are kind of aligned with the weight vector. They'll always be classified as positive because this value will always be positive, right? So I will leave it as exercise for you guys to check, to verify that. And otherwise, all the examples on the other side of this classification boundary will be classified as negative because their angle, say any negative example here, right? Their angle between the weight vector will be over 90 degrees, right? Or pi over 2. Right? And this is a geometry view of our linear classifier. Remember, any linear classifier will correspond to such a classification boundary. And another thing we need to be aware is that actually during the classification, we'll only care about the sign, not the magnitude. It implies that no matter how we skew up or skew down B, W1, W2, it doesn't change the classification results for any example, right? You can multiply them by 1, 1.5, 100, 1 billion, or 0.1, 0.001, right? As long as not multiply them by 0, your classification results are the same. The classification boundary doesn't change at all. Right? So in a two-dimensional space, meaning in a plane, our classification boundary corresponds to a line, right? For sure. Right? In a three-dimensional space, what does it represent?
A plane.
Yes, a plane, right? In three-dimensional space, it represents a plane. And in general, n-dimensional space, right? This classification boundary is represented by a hyperplane because it's actually not a plane, but more intuitively, we view it as a hyperplane. And this hyperplane separates the whole instant space into two half spaces. There's some kind of terms in geometry. Okay, so this is a geometry view of linear classifiers. Any questions so far? Great. So although we know the full representation of our linear classifiers should be the inner product between the weight vector and the input feature vector plus bias term B, right? But in practice, right, for convenience, we often stop writing the bias term explicitly. Instead, we rewrite the input X by augmenting with a constant feature 1 and insert the bias term B into the weight vector. So we got a new feature vector X prime and new weight vector W prime, such that we can write our prediction rule as sine of W prime transpose X prime. Yeah, in most cases, we just write our linear classifier in this way, right? But just be aware, sometimes we need to explicitly spell it out. And also remember, such a bias term B and constant feature 1 do exist in this simplified notation. This is just notation sugar. Any question? Any question? Okay, great. So this is the definition of linear classifier. In the next few weeks, we're going to talk about the several learning methods to identify the parameters of our linear classifiers. namely how do we identify the weak factors in the bias parameter B, right? So we're gonna first look at the perceptron. It's kind of like you can view it as like grandfather or grandpa of deep neural nets. So you see that it's an error-driven learning or lazy learning approach. It's very simple, and it only updates the hyperplane, the classification hyperplane, when there is an error. Then we'll come to a more complex linear classifier called support vector machines. So you see that actually we define a loss function, which includes not only an error term in fitting the training data, but also another term which regularizes the position of your classifying boundary. And this principle, we call it structure risk minimization, right? And then we'll talk about like two probabilistic linear classifiers. One is called naive Bayes classifier, which we'll say it can be formulated as a generative probabilistic model. And another very common used probabilistic classifier, logistic regression. You see that the prediction of logistic regression is just the probability rather than 1 or 0. And this classifier is called discriminative classifier. And in addition to classification, another type of task is regression, right? So when we use linear models to perform regression, we call our model as linear regression. So the task is to predict real value outputs, right? Again, for linear classification, our task is to predict discrete labels, -1 or -1 or 1 and 2 categories. Then it becomes the multi-class classification. Right? So it's just definition of the tasks. So now we have finished the introduction of the linear classifiers definition and linear models definition. So the next topic we're going to discuss is the expressiveness of linear classifiers. Namely, what kind of functions can linear classifiers well represent and what kind of functions they cannot represent. So we'll illustrate how linear classifiers are expressive by using Bloom functions as an example. Just like we use decision trees to represent Bloom functions, right? To see how decision trees, how flexible decision trees are, right? So here is a summary. So linear classifiers are kind of expressive hypothetic class. However, it is not as expressive as decision trees. We'll see that many Bloom functions are linearly separable, but not all of them. By contrast, remember, we discussed before, right? Decision trees can represent any Bloom functions. Right? So now let us start with some positive example, right? Where they can be well represented by linear functions, right? So we'll talk about conjunctions and disjunctions, right? Let's start with conjunctions. Suppose we have a Bloom function, which is a conjunction of 3 Bloom random variables, x1, x2, and x3, meaning that x1, x2, x3, they can choose either zeros or ones, right? So we can use a table to represent the whole function, right? Where each row represents the possible choice of x1, x2, x3, and y is the corresponding function value, right? So because this is a conjunction, only when all x1, x2, x3 are ones, our function output is 1, right? So now, my question is, can we use a linear classifier to perfectly separate all the positive examples from the negative examples? Actually, only have one positive example, right? Can we use a linear classifier to separate this positive example from all the negative examples?
Yes.
Okay, how can we do that?
It's at one corner of the cube. So we just need to find a plane like very close to 1, 1, 1. And anything above that plane is positive. Below that plane will be negative.
Yes, yes. I mean, your illustration is totally correct, right? So from like geometry view, right? So you can think of this x1, x2, x3 are like points in the 3-dimensional space, right? So they are they are positioned in a way that if we can adjust our hyperplane, we can well separate all the positive examples from negative examples, right? So now the question is that how can we identify this hyperplane? What is the parameter, right? Say what is the weight vector? What is the bias parameter? How can I identify their parameters?
Use W1, W2, W3 as 111 and bias as the distance from 0 to 000 to the point 111. It will lie exactly on the plane. Like I'm imagining that we design a plane which actually passes through that point and none of the others.
Yeah, that's a good point. Yeah, that's a good point. Your solution is definitely feasible. Yeah, it's definitely feasible. Actually, we have like numerous planes can well separate positive examples from negative examples, right? So, but now I want to talk about even easier way. So we start with the rule of predicting y, right? So how can we generate rule of predicting y, right? We know that from this function, right? We know that y equals to 1 if and only if all x1, x2, x3 are 1. That means if and only if x1 plus x2 plus x3 is no less than 3, right? Why? Because x1, x2, x3 can either choose 0 or 1s, right? And they're all 1s mean that their summation must be no less than 3, right? Any of them is 0, meaning that y must be 0, right? So this is if and only if. And from this prediction rule, we can construct our linear classifier, right? Our classification boundary is simply you just move 3 to the left-hand side, right? This is our classification function, right? x1 plus x2 plus x3 minus 3, right? Then we just check out the sign of the classification function, right? We see that only when all x1, x2, x3 is 1, you got the classification function to be 0, you got sign 1, right? In other cases, you have sign 0. Meaning that by using this classification function, we can successfully separate all the positive from negative examples. Of course, according to Tushar, you can move this hyperplane for a little bit, right? To have the classification function value even be positive. It is possible. But here we just introduce a most straightforward one. So now my question is, what is the weight vector and what is bias term?
So weight is 111 and bias is -3.
Yes, exactly, right?
Yeah.
Any questions so far? Okay, yeah, I guess this is pretty straightforward. And now we just make a little bit of complication, right? So how about I introduce some negation, right? So now suppose my target function is a conjunction of x1, x2, and negation of x3. Can we represent this function by a linear classifier as well?
Yes.
How?
It will still have only one, like, wait.
You're saying it's correct. You just go one step forward.
It will look, the y will look the same. So just it will be on the 7th rather than the 8th value. Right?
Yes. If you look at table, yes, it is. But what we need to do is to just create another rule, right?
Yeah.
So from this, what we can say is that, okay, y equals to 1 if and only if x1 is 1, x2 is 1, and negation of x3 is 1, right? Meaning that 1 minus x3 is 1. Or in other words, summation of x1, x2 plus 1 minus x3 is no less than 3, right? It's just a little adjustment of the original rule according to negation. Right? And then, we can just arrange the terms and move 3 on the left-hand side. We construct our well-separated linear classifier, right? And we can extend this conjunction to the disjunction case, right? So what if this is y is a disjunction of x1, x2, and x3? How can we construct a well-separated classifier? So when the disjunction is 1.
So we can do the reverse. Y will be 0 if the summation of the points is 0.
Yeah, of course. Yeah, this is one way, right? Another way is that simply we know if it's disjunction, meaning that either any of x1, x2, x3 is 1, meaning that the disjunction is 1, right? So that means we can simply replace 3 by 1. Right?
Yeah.
So that's it, right? Of course, you can use your own rule. You can derive another. I guess it will end up with the same linear classifier. So another type of similarly complex functions can also be represented by linear classifiers called M of n rules. Right? So what is the M of n rules? So suppose we have n Bloom variables, and output y is true if and only if at least m of them are true. All the other variables are ignored. To give a concrete example, suppose there are 3 Bloom variables, x1, x2, and x3. And what is a linear classifier, which is equivalent to the classification rule where at least 2 of this x1, x2, x3 is true? How can we represent this as the linear classifier? We can use the same trick, right? So because at least 2 of them are true, meaning that their summation must be no less than 2, right? When the output is true, or when the output is 1, right? In general, we can just requesting x1 sum over to xn is no less than m. Right? This is equivalent to the case where the output is true. Any question? Okay, great. So, however, not all functions are linearly separable. Here we give some kind of encouraging examples, which you can simply build up a well-separated hyperplanes. Right? But for other functions, you might never be able to find a perfect classifier. Like when you're training examples, X-based some kind of parity. What do you mean by parity? So you say, here's the distribution of our positive examples and negative examples, right? They're kind of like diagonally symmetric, right? So we'll find that you'll never be able to find a hyperplane which can separate all the positive examples from negative examples. You can try, right? You can try here, you can try here, you can try here, and try here. No, you'll never be able to do that. This is actually can be proved, actually. In a general case, right? Let us talk about Bloom function, right? So XOR, this is kind of like common Bloom function. So what is XOR? If we calculate XOR function between 2 Bloom variables, x1 and x2, when the XOR is true. Can anyone remind me? Only when x1 and x2 are different, right? Either x1 is 1, x2 is 0, or x1 is 0, x2 is 1. Then your output is true. This is called XOR, right? So XOR is very commonly used Boolean operator, right? But unfortunately, for this XOR function, you cannot find an equivalent linear classifier where you can separate positive example from negative example. If you write the distribution of examples, you'll see this part and this part. This part and this part will be the this part and this part will be the positive example, and this part will be negative example. Right? And in general, like if you define a Boolean function which X-based parity, meaning that if the number of ones in your input Boolean variables is even, then your output is even. Such kind of functions, you'll never be able to find a linear classifier which can well separate all the positive examples from negative examples. This is proved by Marvin Minsky, a pioneer in artificial intelligence. I think in 1970s, he published a book, a well-known book, which kind of like brought the AI, artificial intelligence, to a second winter. And in addition to XOR and parity, right, many other non-trivial Boolean functions are not linearly separable as well. So basically, that means not all functions are linearly separable, even in the Boolean function family. But by contrast, decision trees, as we discussed before, can well fit all the Boolean functions, right? So decision trees, in principle, are more flexible than linear classifiers. However, with the development of machine learning, people found that even those functions in the original input space are not linearly separable. By using some kind of feature augmentation and feature mapping, you're going to be linearly separable in the new feature space. How can I achieve that? So here, just to give a quick introduction, and we're going to discuss in detail on Thursday, right? So we can re-represent each input point by augment the original input by extra feature, right? Take square of the input. And then you map all the inputs in a two-dimensional space, right? In the original space, it's in one-dimensional. You'll never be able to find a line to separate the positive examples from negative examples, right? But now, after you augment your input features by extra x squared, right? In your new feature space, it is well separated by a line. So this trick is called feature mapping. And in general, it leads to an important trick called kernel trick, which we're going to discuss in detail when we talk about support vector machines. Okay, let us stop here today and see you on Thursday.